So, good afternoon everyone. I am Ninad. I am an MSc student here. So, I'll be talking about probabilistic methods in combinatorics. So, up until now, you would have seen a lot of techniques used to enumerate combinatorial structures in a problem, like the pigeonhole principle or inclusion-exclusion principle, or maybe even recurrence relations. So, the probabilistic method is one such powerful tool which is widely used in combinatorics to enumerate or find a bound on some structures. So, I will just refresh your memory just in case. A probability space is a tuple of 3 elements where omega represents the sample space, which is a set of all outcomes. F represents the event space, which are the set of outcomes which we are interested in, and P is a probability function which maps an event to a real value between 0 and 1. So next, what is a random variable? A random variable is a function which maps an outcome to a real number. So there was a talk on probability before, right? I'll just refresh it once again. So let x be the sum of the numbers which appear when I roll 2 dice, right? So what all possible combinations can I have? Right. So now I'll associate a real value with every outcome. Over here, the random variable indicates the sum of these numbers. So this is 2, this is 7. So I'll go on like this. So when I look at random variable x is equal to 2, it looks at all such outcomes where the sum is 2, and I associate a probability with this. Next, we look at the expectation of x, a random variable, where intuitively it is the weighted mean of the values which a random variable can take. So you sum over all the values of a random variables and the probability that it happens. So now I'll give a small introduction as to how probabilistic method works. So when we look at a problem, we try to construct an appropriate probability space there and then explore the combinatorial structure such that whatever properties we want that occurs with a positive probability. I know this is a very abstract definition, so I'll as and when I give examples during this talk, it will be more clear. Fine. So this was pioneered by Paul Erdős. He, I think a lot of people would have heard his name here. He's one of the most prolific and one of the greatest mathematicians. So he is basically a Hungarian mathematician who has done a lot of his work in discrete math, and most of the problems which we look at have been started or conjectured by him. So why do we look at this? When we already have so many techniques, why do we even need the probabilistic method? So we need situations where rather than finding a constructive structure is difficult, and we need existential proofs in that case. For example, suppose someone looks at the problem of finding an independent set in a graph. I hope everyone knows an independent set. I'll just recap it. So given a graph, an independent set is a set of vertices where none of the vertices have an edge between them, right? So suppose someone makes a claim that given any graph, I will find an independent set of at least this size, right? Why should it be true? I mean, why can we not improve it? So in that case, I need, how do I even prove this? So what I will do is, I will give a graph and say, look boss, whatever happens, this this graph has an independent set of at most this size, right? So in that case, you need to give a bound which such that it matches with the lower bound, or if there's a big gap, you can try to improve. You know that there's something better which can be done with your method. So what we do in the probabilistic method is, we try to prove that instead of actually constructing something, we show that for a given random construction, we can always find something with a positive probability. So if someone asks me how to find it, or what are the, in the graph example, what are the vertices, I cannot say it. But what I can definitely say is, so there exists a set of vertices which gives me this bound. So another useful motivation for this is, if someone makes a claim, you can easily find a random construction and maybe show a counter example for the claim. Another important motivation is the design and analysis of randomized algorithms, which on which there will be a talk in the next couple of hours, and it will be explained better there. So until now, everything I have explained is pretty abstract and generalized. So we'll dive into a few examples, and maybe we can understand how, at least, and get a start as to how the probabilistic method works. So first problem, which I will be looking at, is the hypergraph 2 coloring. So what is a hypergraph? So all of you are familiar with graphs, right? So a hypergraph is a generalization of a graph where you have a set of vertices and a set of edges, which is a subset of the power set. Power set being the set of all subset of the vertices, right? For example, this would be a hypergraph where my set of vertices are V1 to V7, and E1 is an edge which contains V1 to V3, E2 contains V2 and V3, E3 contains V3, V5 and E6, similarly E4, and V7 is not present in anything. So another concept associated with this is an R uniform hypergraph, where each edge in the hypergraph has a fixed cardinality R. So the graphs which you have seen before are two uniform hypergraphs, right? So every subset has size 2. A 3 uniform hypergraph can look like this, for example. So as an exercise, can anyone tell me what structure this represents in a graph? This hypergraph. So, sorry? Okay, so it looks like a cycle, right? You have a cycle here. This is a hypergraph representation of a cycle. So, has everybody encountered graph coloring before? Okay, I'll just define it again for people who have not. So, graph coloring problem is one where I assign colors to the vertices such that no two vertices which share an edge have the same color. And if I can assign a set of colors this way, we call this a proper coloring. So this is a vertex coloring version. So two coloring problem here is, can I color a graph with two colors? Now we look at the generalization of this to hypergraphs, where we look at an R uniform hypergraph and ask if it has a proper two coloring. So what kind of generalizations can anybody think of, just out of your head, at the top of your head? A direct generalization of whatever we saw in the simple graphs. Anyone? Okay, sure. So one way which you can think of is, in every edge there are R elements. So every element has a distinct color. Another way which we can look at is, you pick every edge. Every edge has at least one element with a different color. So I'll be looking at the second version where, where every edge, so a two coloring of a hypergraph is proper if whenever I take an edge, it contains at least one element having a different color. For example, we look at this hypergraph. So every line of a different color represents an edge here. If you look at this edge, it has one vertex having a different color. However, if you look at this edge, so all the vertices have the same color. So this is not a proper coloring. So for a proper coloring, every such edge needs to have an element which has a different color. So is everyone following me until now? Okay, so I'll so let f of r be the minimum number of edges an R uniform hypergraph can have, such that it has no proper two coloring. So as an example, what is f of 2? Where 2 is the cardinality of every edge. What is the minimum number of edges? So in this case, if I look at f of 2, it means what is the minimum number of edges a simple graph can have, such that it is not two colorable. I cannot color its vertices properly with two colors. Seems to be a simple exercise. Can anybody think? So, okay, you look at a triangle here. Can I color this with two colors? I cannot, right? I need three colors at least for this. So basically this means that f of 2 is equal to 3. I need at least three colors. So rather I need at least three edges in a graph for it not to be two colorable. So this problem is a generalization of that, where f is in terms of r, where the cardinality of every edge is r. So this was a theorem by I don't know whom. So every R uniform graph with less than 2 power R minus 1 edges has a proper two coloring. Which one? Yeah, this is for hypergraph. Okay. No. So at least one vertex has a different color. Yeah. So since this is two colorable, we are looking at two colorable. So at least one vertex has a distinct element, different color other than the element. So I look at an edge, right? Maybe I'll go back to the previous slide. I look at this edge, for example. At least one element has a different color, right? Okay, this one, okay. So you look at this edge, you look at this edge, and you look at this edge, right? So you need two colors for this. You cannot color this as one because it will clash with this. You will have a monochromatic edge set. So for an R uniform hypergraph, f of r is at least 2 power r minus 1, which means that if I take an R uniform hypergraph, I need at least 2 power r minus 1 edges for it not to be two colorable. So we will prove this by using a random assignment of colors. So how do I do this? I take every vertex of the hypergraph, toss a coin. If it is a head, I assign it the color red, for example. If it's a tail, I assign it a color blue. So we'll take the probability, let this be a fair coin, and the probabilities are half. So let us consider an R uniform hypergraph with strictly less than 2 power r minus 1 edges. So we color the vertex set randomly using two colors. Now let us look at the event where an edge E is monochromatic. So what do I mean by monochromatic? All the elements in the edge have the same color. So what is the probability of this happening? Note that we are assigning the colors independently. Just we toss a coin at every stage and assign a color. Any suggestions? Okay, so I look at an edge. It has R elements. What is the probability? Let us look at the color red, for example. What is the probability that this has the color red? It is half. Now what is the probability that the next one also has the color red? It is again half. So we go on. Yes, it's 1 by 2 per r. Is this it? Is this the probability of A? So one thing which we are missing is all these colors could also be blue. Right? It's still monochromatic. So this would be 2 times 2 power r. Sorry? Yes, 2 power 1 over 2 power r minus 1. Right, which is 2 power 1 minus 1. Fine. Now we look at the event A, which is the event that at least one edge is monochromatic. Fine. So A is A even fine. So what is the probability that this happens? So what we use is a technique called the union bound of bounding the probabilities in this case, where a simple realization would be a Venn diagram. Let us take just 2 elements, A1, A2. What is the cardinality of A1 union A2? It is A1 plus A2 minus A1 intersection A2. Right. So this would be is this clear? Yeah. So this is just a generalization of that. If you look at the inclusion exclusion formula, you can get it easily. So basically what we look at here is so you will have to enumerate a lot of these possibilities, right? We'll get there eventually. We'll get there. Give me a minute. I'll come there. Fine. So over here, so this is our probability, and this would be, so there are strictly less than 2 power r minus 1 edges into 1 by 2 power r minus 1. So this is strictly less than 1. So what does this indicate? This means that the probability that our hypergraph has at least one monochromatic edge is strictly less than 1. So if we invert this, okay, see it better now? So this level, is it? This is fine. Sure. Yeah, I'll do that. the probability that at least one edge is monochromatic is strictly less than 1. So what is the complement of this? The complement event is that none of the edges are monochromatic, right? So we get the probability that none of the edges are monochromatic is greater than 0. This is strictly less than 1. So the probability that none of the edges are monochromatic in a 2 coloring is strictly greater than 0. Thus we have shown that we can find a proper 2 coloring without monochromatic edges. So any doubts until now? Okay, maybe I'll move on. So note the key point here that we just showed the existence of a coloring. So if you ask me to give this coloring, I cannot, because I just use a random assignment and I don't know what coloring gives me a proper coloring. However, I do know that it exists. So these are the kinds of proofs which we'll deal with in the probabilistic method. Fine. So I'll move on to the next example. Before that, let us look at property of random variables and its expectation. So a linearity of expectation says that the expectation of two random variables x plus y, so these could be independent or dependent, it doesn't matter, would just be the summation of their expectations. Generalizing this, we have expectation of CIXI for over n random variables is just Ci times expectation of xi over everything. Is V not true? So what we looked at was, let us take the set of events where at least one edge is monochromatic. Fine. Now this probability is strictly less than 1, right? So what is the complement event of this? None of the edges are monochromatic. That is what we want, right? So what we want is that every edge has at least one element having a distinct color, which means it is not monochromatic. So if we prove that there is a non-zero probability of this happening, we say that there exists a random coloring, a 2 coloring of this. Right? Yeah. So expectation is a weighted mean, right? So for example, when you look at the heights of the people in a class, when you look at the mean of this, you can definitely say that there exists one person, at least one person, whose height is greater than or equal to the mean, and similarly less than or equal to mean. Is this fact clear? This seems intuitive. So when you look at the expectation E of x, you can make a similar statement that there exists a point in the probability space for which the value of the random variable is greater than or equal to E of x and similarly less than or equal to E of x. So we'll be using this in the further proof. I'll give an explanation as to how. So has everyone seen the satisfiability problem? Okay, so satisfiability problem is that given a Boolean formula of n variables, does there exist an assignment to these variables such that the Boolean formula is true? Right. So this problem is one of the first NP complete problems. So we look at a further constrained version of this, which is called the 3 satisfiability problem, where a Boolean formula is in conjunctive normal form if it is the AND of ORs. Right. You have ANDs here, and each clause has ORs, and the constraint here is that each clause has 3 literals. Right. So the problem is that can such a Boolean formula be made one by giving an assignment to these variables? So even this problem is NP complete. This would be an example for this 3 satisfiability problem, where you have 3 literals here which are ORs, and you have an AND of these clauses. So now we know that this is NP complete. We look at another version of this problem and call it max 3-sat, which is given a 3-sat formula, can we find a truth assignment such that maximum number of clauses can be satisfied. Just slightly relaxing the previous one. So this is also NP complete because the maximum you can satisfy are all the clauses, right? So again, max 3-sat is not an easy problem. So what we can do is, by giving a random assignment to the variables. What do I mean by a random assignment? I just set it to 0 or 1 by a coin toss. I toss a coin. If it is head, I set it to 1. If it is tail, I set it to 0, and it's a fair coin. So what I will prove that if I give a random assignment to these variables in a 3-sat formula, I can always show that there exists a truth assignment which satisfies at least a 7/8 fraction of all these clauses. I cannot solve all the clauses maybe. I'll try to solve as much as possible, and I can with a random assignment I can give a bound for this. So as I said, each variable is set to 0 or 1 independently, its probability half. So we'll use a random variable for every clause in the formula, right? So there are m clauses, n variables, so I have m clauses here. So I'll assign a random variable to each clause, x1, x2, go on, I'll have xm. Fine. And I'll set this random variable to 1 if any of the three literals in the clause is set to 1 by the random assignment. Fine. Or otherwise it will be 0. So what is the expectation of this random variable? It is 1 times probability that xi is equal to 1 plus 0 times probability that xi is equal to 0, which is just probability that xi is equal to 1. This means that probability that by a random assignment this clause is true. So can anyone give me this probability that xi is equal to 1? So just enumerate all possible combinations of three literals, and can anyone give me this? Sorry? It's 7 by 8. So we are looking at probability that clause is satisfied. So any one of these variables can be set to 1 and it's still satisfied. So this is 7 by 8. So the expectation of xi is 7 by 8. Now I'll pick a random variable x, which is the sum of all these clause random variables. So what does this mean? What does this random variable indicate? So it's a random variable where the event is the number of clauses satisfied by the random assignment, right? So depending on what values xi take, x gets a value. So now let us take the expectations of this. Note that these xi's are not actually independent. So setting setting a variable 1 could mean that I'll be setting a variable 0 here. I could have x3 bar somewhere. So this would be x expectation of this. Right. So now we'll go back to whatever we saw in the previous slide, the linearity of expectation, and we see that this would be fine. So what does this give me? The expected number of clauses which are satisfied by my random assignment is 7m by 8. So now we'll use the idea that there exists a point in the probability space such that whose value is greater than 7m by 8. And now what this shows that there exists a random assignment such that at least 7 by 8 fraction of the clauses are satisfied. So is this step clear from going from here to here? Yep, if there are any doubts. So again, we look at an existential proof where if you ask me the assignment, I cannot give it to you. However, I can just show that with whatever assignment, rather not whatever assignment, we can always find an assignment such that 7 by 8 fraction of the clauses are satisfied. So I'll move on to another example. So this is called the dominating set for graphs. So a dominating set of a graph is a subset of vertices such that given any vertex in the graph, it is either present in this subset or it is a neighbor of a vertex in this subset. So I'll make this more clear with examples. So look at this graph. So the red vertices form my dominating set because you look at any of the other vertices, they have a neighbor to at least one vertex in this set. So similarly, these two would form my dominating set here, and these two would form my dominating set here. Where if you look at any of these vertices, they have a neighbor in this set. So as an exercise, you can just try this out. So can anyone give me the dominating set for this? A and D. Is this minimum? This is the minimum dominating set here. So the problem of finding the minimum dominating set is again NP complete. So what we look at in our talk is to find an upper bound for the dominating set for all graphs having a minimum degree which is fixed. So let G be a graph on n vertices with minimum degree of every vertex being D. D can be any value greater than 1. So this means that for any graph G which has a minimum degree D, I can always find a dominating set of size at most n times 1 plus log of D plus 1 divided by D plus 1. So this log is the natural log should be log to the base e. Right. So we'll go to the proof of this. So again, we'll start off by taking a random subset of vertices. In this case, this is equal to tossing a coin. Rather than that being a fair coin, it will be a biased coin where the probability of heads is p and tails is 1 minus p. So if I get a head, I'll add it to my set. If not, I will not. So let X be this randomly chosen subset of vertices, right? So I'll associate a random variable xi with each such vertex such that if xi is 1, then rather if I add the vertex to x, then I set xi to 1, otherwise I set it to 0. So there are just two possibilities. I add it to my subset or I don't. So now, what is the expectation of xi? Can anyone tell me this? So we are doing this with the probability p, not half. Huh? Just xi, right? So it's just p. 1 times p plus 0 times 1 minus p. So this will be p. So we'll define another random variable, capital X, where this random variable indicates the number of vertices which I have added to my chosen subset, chosen random subset. So what is the expectation of X now? We can use the linearity of expectation to find this. So can anyone give me the expectation of X? It's there. So yeah, it's just NP. Is this clear to everyone? As to how we are choosing the random variable and why we get the expectation as NP. So just think of this as using a biased coin rather than an unbiased coin here. Okay. Yes, of course. We are looking at the minimum size. So the minimum size is upper bounded by this for any graph. For any given graph, if I look at the minimum size, it is upper bounded by this. So will this random subset which I have chosen form a dominating set? So these are just some random set of vertices. These need not dominate every neighbor. By dominate I mean either the vertex is present in D or its neighbor is present in D. Right. So in this case, let us pick, we need to make this as a dominating set and we need to add a few more vertices to do so. So what we'll do is, we'll look at the set of vertices. So if this is my randomly chosen subset, we look at the set of vertices v minus x, fine, and pick that subset from here such that it has no neighbors in x. For example, suppose by my random experiment I chose these vertices to be set x, right? So these form v minus x, now I pick those vertices from v minus x which do not have any neighbor in x. So that would be this vertex and this vertex. So let me put this in a subset called y. So is the definition of y clear? So now I will claim that X union Y is a dominating set. Can anyone say why? So, set of vertices in V minus X, so they are either neighbors of X or they are not. So, if we look at the neighbors of X, we are not adding them. We are adding only those vertices which are not the neighbors of X, right? So, X union Y must form a dominating set, because basically we are adding those neighbors, those vertices to this which are not neighbors of X. So, we are covering all vertices here. So, next I will associate a random variable yi, sorry, I will associate a random variable yi with every vertex. So, what does this indicate? It is set to 1 if the vertex ends up in y through my random experiment, otherwise it is set to 0, in which case either it belongs to X or it is a neighbor to one of the vertices in X, right? So, I hope the definition of yi is clear. So, this is the crux of this argument. So, now what is the expectation of yi? So, this should be 1 times probability that yi is equal to 1 plus which is just probability that yi is equal to 1. So, what would this be? So, let the minimum degree of every vertex is d. Sorry? 1 minus p plus pd is not right, right? So, yi is a case where for a given vertex it is not present in X and none of its neighbors are also in X. X is my randomly chosen subset. So, I is not present in X, I is not even a neighbor of any vertex in X. 1 minus? Actually, so there's something slightly off there. So, what this would be is, let me take the vertex I. So, probability that it is not in X is 1 minus p, and since none of its neighbors are also in X and d being its minimum degree, it is 1 minus p power d, and we have the degrees at least d, right? So, this would be at most this. So, this will just be 1 minus p power d plus 1. So, this is the probability that a given vertex I is not present in Y. So, we will write this. So, is this probability clear? So, probability that a vertex I is not present in Y is just that it itself is not present in Y. Probability that that happens is 1 minus p, and none of its neighbors are present in X, which is 1 minus p power d. So, it has d neighbors and none of them are present. So, this will just give me 1 minus p power d plus 1, and since the expectation of yi is just this, so expectation of yi is again 1 minus p to the power of d plus 1. So now we use a similar trick once again, where y would be summation yi, where the random variable y would indicate the number of vertices which are present in y. So this would be n times fine. Is this clear? This comes again from the expectation of y. This comes again from the linearity of expectation. So we already proved this, that x union y, which is u, is a dominating set. Now let us look at this random variable. So this gives me a size for the dominating set, right? Since x and y, their union forms a dominating set, this gives me a size for the dominating set. I look at the expectation of this, which is at most np plus n times p to the power of d plus 1. This would be So is this clear? Now we use the fact that 1 minus p is at least e power minus p. Why is this true? If you take the limit as n tends to infinity, 1 plus x by n, the power of n, this would tend to e power x. Right. So over here n would be 1 and x would be minus p. So you just get 1 minus p at most e power minus p. Fine. So we just substitute this. So what this gives is we have right. So now note that we have not found p yet. P is just any real number between 0 to 1. So to find the minimum size of the dominating set, we need to minimize this expression such that our upper bound is as good as possible. So if the value of p is minimum, then suppose we would have a value x, right? For any other value of p, we would have a value y. So if you are looking at the upper bound, finding the value of x is the best one we can do. So we minimize this expression for p. This is using the standard differentiation argument, and see that p is so I won't go over differentiating this, it's a tedious calculation. However, I think if you are interested, you can try it out. So plugging in this, we get that the size of the dominating set is at most n times 1 plus ln of delta plus 1, the entire thing divided by d plus 1. So again, I am stressing on this, we have an existential proof here. We don't know what the dominating set is, what a random subset is, but I have still shown a bound for every single graph with a minimum degree d, that I will always find a dominating set of this size. Fine. So one more thing, as to, so there are researchers in the world who are looking at trying to find algorithms for this existential proofs, and in some cases they have been successful. So we also have constructive proofs now for this. So what I gave in this talk was just an introduction, a gist of how we would start in using the probabilistic method for enumerating structure. So the best reference for this book would be the probabilistic method by Alon and Spencer. And yeah, with this I will end my talk. Thank you. So, any questions? Yeah, I think I should. Thank you once again.